Namaste and welcome back to JEE Physics with Typical Monk. This is Class 20, Electromagnetic Induction. Faraday found the deepest bargain in physics. Move a magnet near a coil or a coil near a magnet, and electricity simply appears, paid for by the work of moving. A changing magnetic flux is the trigger, and nature, ever contrary, always fights the very change that creates it. Today, the laws of Faraday and Lenz, the motional EMF, inductance, and the slow growth of current in a coil. One idea at a time. Here is what you will learn today. First, magnetic flux and the laws of Faraday and Lenz. Second, the motional EMF and eddy currents. Third, self and mutual inductance. Fourth, the energy in an inductor and the growth and decay of current in an LR circuit. And fifth, the alternating current generator plus the drills. One idea at a time. 4 ideas. Run this entire chapter. Look at them together first. Magnetic flux. It is B times A times cosine theta, the amount of field threading through a loop. Faraday's law. When that flux changes, an EMF appears. The EMF equals minus the rate of change of flux minus dφ by dt. Lenz's law. That is the meaning of the minus sign. The induced current always opposes the very change that produces it. And the time constant. Tau equals L over R. The pace at which current grows in a coil. Now, look at the picture. A rod sliding on rails. The simplest source of a motional EMF. The motional EMF 5 slide a rod of length L along 2 rails at a speed v through a field B pointing into the page, and an EMF equal to B LV appears across it. Why it appears? As the rod moves, it sweeps out area, so the flux through the loop changes, and Faraday's law then delivers the EMF F. The current. If the circuit is closed through a resistance R, a current flows. I equals the EMF over R, which is BLV over R. And Lenz's law. The induced current opposes the motion, so a retarding force acts back on the rod. You must keep pushing to hold its speed steady. Now the working formulas, the ones the exam turns into marks. The ribbon holds the anchors. Faraday's law, the motional EMF, and the time constant. Faraday and Lenz. The EMF equals minus dφ by dt, and the flux can change in 3 ways: through the field, through the area, or through the angle. Self-inductance. The EMF equals minus L times di by dt, and the energy stored in an inductor is 1/2 Li squared. Mutual inductance. A changing current in one coil induces an EMF in a neighboring coil. The EMF equals minus m times di by dt. And eddy currents. These are swirling currents induced in a solid block of conductor. They are used in braking, and their energy is dissipated as heat. Let us work the G favorite, a rod on the rails. A rod of length 0.5 meters moves at 4 meters per second on rails in a field of 0.2 Tesla with a circuit resistance of 2 ohms. The setup. Rod length L is 0.5 meters, speed V is 4 meters per second, field B is 0.2 Tesla, and resistance R is 2 ohms. The EMF, it equals BLV 0.2 times 0.5 times 4, which is 0.4 volts. The current, I equals the EMF over R, 0.4 over 2, which is 0.2 amperes. The retarding force, F equals BIL 0.2 times 0.2 times 0.5, which is 0.02 newtons. You must push with exactly this to keep the speed steady. And the power, P equals the EMF times I, 0.4 times 0.2, which is 0.08 watts, and it equals I squared R, the work of your push turned into heat. Now the picture of current building up in a coil, the LR growth curve. The growth, close a switch, and the current does not leap to its maximum. It rises smoothly as I equals I naught times bracket 1 minus e to the minus t over tau, where I naught is the EMF over R. the time constant, tau equals L over R, and in exactly one time constant, the current reaches 63% of its final value. While the delay, the inductor resists the change, inducing a back EMF that opposes the rising current and slows it down. And the decay, open the switch and the current falls the other way. I equals I naught times e to the minus t over tau. And after about 5 time constants, it is essentially gone. Now what JEE actually asks. 5 pointers. 1. Faraday, the EMF equals minus d phi by dt, and Lenz, the induced current opposes the change that produces it. 2. The motional EMF equals BLV. The current is BLV over R, and the retarding force is BIL. 3. Self-inductance, the EMF equals minus L di by dt. The energy is 1/2 Li squared, and the time constant is L over R. 4. Mutual inductance, the EMF equals minus mdi by dt, the working principle of the transformer. And 5. Eddy currents induced in bulk conductors and used in braking and in induction heating. Now an assertion and reason drill. For each pair, are both true, and does the reason explain the assertion? First pair. Assertion. A changing magnetic flux induces an EMF in a loop. Reason. The induced EMF equals the negative rate of change of the flux. Both are true, and the reason directly explains the assertion. That is Faraday's law. Exactly. The answer is A. Second pair. Assertion. In an L circuit, the current reaches its final value instantly when the switch is closed. Reason. An inductor opposes any change in the current through it. The reason is true, but the assertion is false. Because the inductor opposes the change, the current rises only gradually, over time. The answer is D. Third pair. Assertion. Eddy currents are used in electromagnetic braking. Reason. Copper is a good conductor of electricity. Both are true. But the braking works through the retarding force from Lenz's law, not merely because copper conducts well. So the reason does not explain the assertion. The answer is B. Now match each quantity to its formula. Faraday's law goes to minus d phi by dt. The motional EMF goes to BLV. The inductor's energy goes to 1/2 Li squared. And the time constant goes to L over R. 4 pairs, each worth committing to memory. Now, how many of these 3 statements are correct? 1. The induced current opposes the change in flux. That is Lenz's law. That is correct. 2. In an LR circuit, the current reaches its maximum instantly. That is wrong. It rises gradually. 3. The energy stored in an inductor is 1/2 Li squared. That is correct. So the answer 2 are correct. Statements 1 and 3. The trap is statement 2. In an LR circuit, the current rises gradually, not all at once. Now the 2 mistakes that quietly cost marks. The myth. The induced EMF depends on the flux itself, not on its rate of change. The truth. It is the rate of change that matters. The EMF equals minus d phi by dt, so a large but perfectly steady flux induces nothing at all. The second myth. In an LR circuit, the current appears at its full value the instant the switch closes. The truth. The inductor opposes the change, so the current grows gradually with a time constant tau equal to L over R. Now, test yourself. Answer in your head before the reveal. That is how JEE speed is built. Here we go. Question 1. The formula for the motional EMF BLV. Question 2. The time constant of an LR circuit, L over RBR. Question 3. The energy stored in an inductor, 1/2 Li squared. Question 4. The current after one time constant, as a fraction of the final, 63%. And question 5. Faraday's law, the EMF equals minus d phi by dt. Let us gather it all in one breath. Faraday, the EMF equals minus d phi by dt, and Lenz, the current opposes the change. The motional EMF equals BLV. The current is B LV over R. The retarding force is B IL. Self-inductance, the EMF equals minus L di by dt. The energy is 1/2 Li squared. The time constant is L over R. The Lr growth, I equals I naught times bracket 1 minus e to the minus t over tau, reaching 63% in one-time constant. Eddy currents, used in braking and induction heating, and mutual inductance, the heart of the transformer. Next class, alternating current, the root mean square values, phasors, and the LCR circuit. A change in flux is all it takes. Motion becomes electricity, and nature always resists the change that made it. No master Faraday, Lenz, and the patient growth of current in a coil and induction holds no more surprises. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time. You will crack G. I will see you in the next class.